Welcome to the 23rd lecture on ECD. In this lecture, we'll study single supply push-pull amplifiers. And in last lecture, we studied the same amplifier, but where here we had a negative VCC. So having a single supply is better than a dual supply because the dual supply has a cost larger than the cost of a single supply. So let's see what this single supply circuit does to the input VCC and what the changes or what modifications do we require. These are the modifications C1, C2 and C3. Now we require these modifications, these three capacitors. Remaining circuit is the same as we studied for dual supply, except we have a ground here in this case, and in the previous case we had a negative VCC here, and the other changes are the C1, C2 and C3, these three coupling capacitors. So why do we require these coupling capacitors? Because now we have to bias this output at VCC by 2. Previously we biased, if you remember, we biased this output at 0 volt, so we didn't need any coupling capacitor. So here we need a coupling capacitor because at this point marked with an static we have this output VCC by 2, swinging at VCC by 2. What we want is we want the same output but swinging at 0 volt reference. So for that we need this coupling capacitor and this input coupling capacitors to stop entering this biasing current into the small V input source. That is, we have studied earlier that if we need this biasing circuit, we have a biasing circuit, we need these capacitors, the coupling capacitors, to stop entering DC to the input and to stop entering this DC to the output. So coupling capacitors are now required. That's the main expense, C1, C2 and C3. This is the extra expense we have to make if we try avoiding this negative VCC. But this cost is smaller than the cost of negative VCC, that's obvious. So it's a better circuit in terms of cost. It costs lesser than the dual supply circuit. So let's see how does it work. R1 with the help of an example. R1, R2 are 470 ohms, VCC 20 volts, RL is 50 ohms. So we have the same RL, 50 ohms. So we have a VCC2 is equal to VCE1. VCE1, the DC VCE1 is VCC by 2, and this VCE2 is also the same, VCC by 2. So we have biased the output at the middle of VCC and ground, that is VCC by 2. So V output peak would be VCEQ VCC by 2, because now this VCE here is VCC by 2. VCE2 is actually the output DC voltage, which is VCC by 2, because we want to bias it in the middle, and our output peak is 200 milliamperes because it is equal to VCEQ over RL. So this, with the help of this small example, we can understand what would be the output peak voltage, what can be the output peak AC current, 200 milliamperes, VCEQ over RL. So that's pretty much like we studied for dual supply circuit, except we have these coupling capacitors, and the output is not biased at 0 volts, but it is at the VCC by 2. Yeah. So this is the main difference. The output isn't, the DC voltage at output isn't 0 volt, but it's VCC by 2. And we have the single supply circuit and these three coupling capacitors. These are three main differences. So let's find out the efficiency of a class AB push-pull amplifier. And we know that the efficiency is the ratio of the output power, AC output power delivered to the load, divided by the input DC power supplied by the VCC source. So V out is V out RMS time out RMS. We know that V out RMS is VCEQ is VCC by 2 in this case and was equal to VCC if in case of dual supply circuit, but whatever is it remains the same for one kind of circuit. So we'll keep it VCEQ. So VCEQ would be VCC by 2 for this circuit for this circuit. VCEQ is equal to VCC by 2 for single supply circuit. For this single supply circuit, VCEQ is VCC by 2. So replacing VCEQ with VCC by 2, this 0.5 becomes 0.25. Now it is 0.25 times VCC times the saturation current IC sat. So this is equation number 1. This is our equation number 1. So what is the second equation? The denominator, because efficiency is the ratio of the output AC voltage to the input DC voltage, or the output AC power to the input DC power. So let's find the denominator. The denominator should be PDC, which is VCC IC sat over pi. Where does this pi comes? This pi come, where does this pi come? Right, this pi comes because the output is a rectified average value. It's a rectified signal. The output is biased at 0.7 volt and the current drawn varies as the input varies. During positive half cycle, the current drawn is like this because the input biasing voltage changes. Initially, it's at 0.7 volt when we have no input signal or the input signal is 0. But if the input signal increases, this voltage also increases. This means IB increases. This means IC increases. So IB and IC, they keep on increasing and decreasing during positive half cycle. And the same happens during negative half cycle. IB and IC, they keep on increasing. So the output current IC would be a full rectified wave like this. It's not a constant current. So VCC isn't supplying a constant current throughout the operation, but the current supplied by the source VCC is also changing as the input voltage is changing. So this is the key point because this increases the efficiency of the class B amplifier or class AB amplifier compared to the class A amplifier. The DC current drawn from the VCC source isn't constant throughout the operation, but it keeps on increasing and decreasing in this way as a full rectified wave. So, and the average value for full rectified wave is IC sat divided by pi. This is what we proved in our LCA course, linear circuit analysis course, where we studied average and RMS values for various signals that are found in many courses in electrical engineering. And the same divided by pi we studied in applied physics course or basic electronics course, where we studied rectifiers. I think we studied rectifiers in applied physics course, where we studied the average value of a half rectified wave, the average value of a full rectified wave. So it's a recap from LCA or basic electronics or applied physics, that the average value of full rectified wave is the max value divided by pi. So we had an integral based formula in which we put the signal, the periodic signal, its time period, and we solve and then we reach to this value. And finally, eta, the efficiency, P out over PDC, the output RMS divided by the input DC power. So plugging these values, this is 1, this is 2. So dividing equation number 1 by equation number 2, equation number 1 divided by equation number 2. It gives us, everything cancels, it gives us 0.25 into pi, that is 0.79. So it has 79% efficiency compared to, very large compared to class A amplifier. For class A, what was the efficiency? Do you remember? It was 25%, right? It was 25%. So compared to 25%, this efficiency is very large. And why is it large? because of this factor pi, because of this factor pi. And where does this pi comes? Because the input VCC supplies current only when it is required. It's not supplying current all the time. So this is actually the key difference. So this pi makes the difference. This pi is bringing a difference, increasing the efficiency eta from 25% to 79%. A significant increase in eta. So you can solve a problem. VCC is given 20 volts, R1, R2 are given, RL is given, and we can find eta. It comes out to be 79%. What should be the Rin? The last thing. Rin for this amplifier. Rin is R1 in parallel with R2. This is what this ACC is, R1 in parallel with R2. The what is the forward bias resistance of these two diodes? That is negligibly small. So R1 in parallel, considering these diodes short, R1 in parallel with R2 in parallel with this RL, and RE is multiplied by beta, because these resistors are on the output side and bringing them to the input side. If we bring them to the input side, we multiply them with beta. So beta times what should be the Rn? Beta times Re plus RL multiplied by R1, but in parallel with R2 in parallel with R1. So this is how we compute the value of the input resistance Rin seen by the source applied to the base of both transistors Q1 and Q2. So Rin is, what is Rin? Rin is this. Rin is this resistance seen by the input source supplied to the base of the two transistors. Rin is the resistance that this source sees. Right. That's all for this lecture. We'll continue studying class B and class AB amplifiers in our upcoming lectures. Right. Thank you.